We are 14.
Okay, okay. So which means that the rest will join. So my name is Adam Shaibu, and I'm here to take you guys through introduction to software engineering. Okay, uh, it's pretty an amazing course, and I will also say a career as such. It's one of these few courses that when you take it seriously, when you have a chance to work or maybe create an employment, which in the area of IT is something that is very important in the sense that now everything is about software. Uh, to travel, you need software to let's say to create an application. Basically, whatever you need to do, you require software. So it's very important to understand the engineering part of software. And as I say, you also take it seriously. I mean, it's going to be the same thing that you'll be doing when you actually get a job or you create an employment. Okay? Yeah. So before, I mean, as we are actually dissecting the program, let me quickly go on to share the course outline, which I've already shared with the class rep today. So, so basically, these are what you're going to do. You're going to look at the introduction to software engineering. Then we're going to look at the type of software and what software engineering is really about, and the legal, the ethics, and I mean much more in the introduction. Then we'll quickly run to the software development cycle. Then to the software process model, requirements, engineering, software design principles, software testing. Because at the end of the day, after developing the software, you need to test it. So we're going to look at all that you require in terms of testing and also quality assurance. Then we'll go into software project management and cost estimation. So if you have a contract with a company, I mean, how are you going to manage and how are you going to look at the cost estimation in coming up with such software? Then, how software is being used, we're going to look at software maintenance and evolution. So before we start the chapter one, if you have any question, be it personal or anything, kindly draw my attention. Okay, if there are no questions, let me quickly jump to the first lecture, which is the introduction to engineering. Okay, so I shall brought the table of contents. Let me see if I have it. Can you hold on? Just give me a moment to okay. Yeah. So we're going to look at just the intro, or yeah, just the intro. What software engineering is. Then we'll go to software crisis and its origins. Then the types of software, attributes of good software, software engineering application domains, professional and legal responsibilities, and modern software engineering and challenges. Then we look at software engineer, the software engineer as a professional. Yeah. Then if there are any questions, then let me know. And I also try to relate to, I mean, contemporary issues and also issues that happen some decade that necessitated uh, some consideration to be implemented in our current environment. So if there are no questions, let me quickly start. Then let's see how far we'll be able to uh, go. All right? So chapter one is the introduction to software engineering. Yeah, I wasn't sure I was available for meeting you guys on the orientation. So as I said, my name is Madam Shaibu. I'm the head of software. So primarily, I manage all the software systems in the school. You understand? So I think there's no need to panic, and we'll actually go slowly. And if I'm moving fast, kindly draw my attention. And if there's any question, feel free. Don't feel like maybe my English is bad and this and that. I mean, I'm here to help you guys. Yeah. So software engineering is a systematic, okay, application of engineering principles, methods, tools to the development, and the maintenance of high quality software systems. So it's actually quite powerful keywords. Okay. So the first keyword that we see here is systematic, which means that we don't do or we don't develop such application just like that. No, it goes through a process. I mean, standard process. So that's what I mean that systematic. It's not something that you just decide, no, 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 no. Even if you decide anyhow in your brains, and then it goes through a process which follow the engineering principles. Okay. So which means that, for example, if you see when to develop a software, maybe you need to go through some aspects of it. It is something which is feasible to develop. Do we have all the tools available? Do you have all the personnel, the resources available? And even the business aspect of it. It is something that when we develop, people are going to use it. Or do we have our target audience in place? Because in this direction, all of these are being factored. Now, the methods. There are so many methods that actually is needed, different methods. And at some point in time, we may blend in multiple methods in order to reach our goal. Now, if maybe we plan that we are going to use a year to develop a software, now maybe we have method one which is working, but at some point in time, the method one is actually taking more resources than required. So we can move to method two, or we can blend in some methods. Now, the tools. The tools, there are so many tools that we use to develop applications. Okay, we have the database, the IDE, the AI, and the rest. Some of the tools are basically free. Some of the tools that you need to buy, and some of the tools that you need to subscribe. And I'm sure most of you may have done system analysis and design. It's actually a part or a subset of the software engineering. So, which means that you need to bring a solid case to which this software must be developed. Then we apply the software engineering skills, principles, and methods and tools that will help develop the system and maintain. Because at the end of the day, you are not the only one in the market who can develop such a software. Now, the emphasis is on the high quality software systems. Just like, I mean, our clothes that we wear. You know, you can't wear fake to, I mean, places and too much comfortable. We try to wear the best quality clothes to the best occasions. So which means as a software engineer, all this you should keep in mind. Because in software systems, you are developing something that the user or the customer will not have nothing but praising your what capabilities. Now, this is a discipline that combines computer science, maths, project management, engineering practices to produce software that is reliable, efficient, maintainable, and meets user requirements. So, which means that it has some computer science in there in terms of developing perfect algorithms or to use the optimized algorithms in order to what develop such a sophisticated system that you want to develop. And basically, computer science and math are two sides of the same coin, or pain or kakra. Then project management, because imagine develop a system for the school, like what you guys are using, the school management system. I mean, I'm not sure any one of you would think that it's being developed by only one person. No, it's actually a team. So, which means that coordination is the key in terms of the resources and the demand that this resource person will require. Now, there are natural causes. Maybe someone may leave the job due to maybe he or she having a better offer, or fee disgruntled, or maybe gross insubordination, or maybe God will take him or her away. What should happen? Should set delay the timeline for the completion of the project is something that the project management seeks to understand. And also the project cost. All of them actually comes part of the project management. Then the engineering practices to produce software that is reliable software that doesn't break down. At the time that you need it, that's when the software should actually show its resilience, efficient. When using, does it take more data? Does it take more than necessary to perform a simple task? And efficient. Maybe does it require more resources to run such application? Now, is it easy to maintain? Because as humans, our needs and want keeps on changing. Today you want this, tomorrow you want that. Today, you understand? So, in terms of software development, as we have our phones, the software that we have keeps on getting update notification every now and then. How easy is it for it to be updated or maintained? Does it require so much resource in terms of even money investment to maintain it? And lastly, to meet the user requirements. Any update that they do is something that is going to be our benefit or not. Once a software company is not able to keep up the demands of their requirement, then they will need to move to another vendor, or they need to develop another software that can meet the user requirements. What are some of the user requirements that I mean here? So if, let's say, we are developing a software company, we are developing a system for a company. First of all, in terms of user requirement, we need to know what the customer wants. The customer may not give you the exact, but based on a storyline, it actually builds some capacity and ideas on how you want it. For example, to register your courses, definitely the system will be developed to register. But then, in terms of its usability, that one the customer may not be silent. Which means it actually depends on your ingenuity to develop such system that even the customer will be mesmerized. For example, you have paid your fees, but due to maybe issues or something that maybe caught you off guard, you have not registered. Now, the system should be proactive to let you understand, oh, Mr. Collins Odro, you have paid your fees, you meet the number requirements for this semester to register the school, but then it's been 24 hours since you paid, you have not registered. So this notification is to remind you. So you could see that you'll be so happy that you will not suffer the penalty for late registration or for non-registration of what? Your courses. So these are some of the silent things that the user may not require, but because of how experienced and how, how experienced that you are in that particular field. So that even if the user forgets, the system is very proactive to remind you. And this is why systems are being built. Because imagine, let's say, you tell your friend, oh, when it's 8 o'clock, wake me up. Trust me, that person, if that person is even more tired than you would rather be waking the person up. But for system, once it has energy inside, it should be able to what? Obey those instructions that you give it to. Now, let's look at how the term engineering or software engineering came about, which everyone you see on his or her timeline, either software engineer or a software developer. I will actually give you a distinction between them. But first of all, let's look at software engineering. So it's actually coined during NATO. NATO is basically North Atlantic. It has some. It's about, I think, the Western countries coming together to share intelligence and all of that. So they have a science committee which was held. So it's actually North Atlantic Treaty Organization. So it's basically for collaboration among member states in terms of security and defense. So one of their committees held a conference in Germany, 1968, specifically in response to what we call software crisis. Because at that time, development of hardware systems were not standardized. So which means that when things are not standardized, then definitely chaos will be what? The end goal. So they actually met to actually discuss what they see like people not having a concrete way of developing software application, which they call the software crisis. So this meeting actually came out that we need to have a formal response to the need for a rigor, structure, and professionalism in software development. So you could see that when you have chaos in a society, at one tipping point, members need to meet to discuss to ensure uniformity, conformity, and standardization on how things are being run in the community. So as a result, we have another organization called IEEE, that stands for Institute of Electrical and Electronic Engineering. So they came out with this definition that says that it is the application of a systematic, disciplined, and quantified, because at the end of the day, even though software is not something that you can hold, but then we quantify in terms of what? How much does it cost? How long does it take to develop, to maintain, and all that it takes? Approach to the development, operation, and maintenance of software. That is the application of engineering toward software. So as a result of that meeting, this is where we came by the term software engineering. So you could see that the development is there, but then the systematic approach, the discipline actually necessitated for this definition. Any question up to this point? Feel free, any question up to this point. Now, from level 100 to now, you may heard of what is a software because if you look at software engineering, it's actually two words which is combined, engineering and software. So engineering is basically the systematic approach of what? Coming out with what? A product. There's discipline, all that, the standardization coming out with what? A product. So the product is basically in the context of what? Software. It is very, very important that we know what is a software and what is what a program. And you all know a program is basically those instructions in various computer languages that is used to perform a specific task. Whereas the software is basically the composition of all that it takes to develop that particular software or that particular application. Let me put that way, that particular application. So you are talking about the program itself, the data that you'll be using, which mostly to be stored in the database, in a file, in an image, in a video. All of those data sources is part of what being called the software. And the documentation, because you may not be the one who will be living forever to maintain that software. So how the software was built, the inside out, you need to document it. So that whoever takes over will know how it was being developed and will understand why the system is behaving the way it is behaving. So software is much broader concept as compared to what? A program. Okay. So the software product is basically the software developed for a specific customer or a general market release. You know, there are softwares which is meant for a specific task. For example, the software used to man aircraft is just basically for that. But for our general purpose operating systems, it's meant for so many things like what we are doing now, playing music, for watching movies, for coding, and all of that. Then the software system is basically those pieces of software that come together, and even to the extent that they help manage the hardware to which it is being installed on. And whereas the engineer is basically the discipline or what the process or the standardization of building and maintaining software systems. Now, I'm sure some of us may be confused. I should have done software engineering or I should have done computer science as a degree program. Now, see the software engineering and computer science this way. You know, if you're going to build a house, the architect will now design it on a paper. Then it will give it to the developer to build. So now the architect is basically the computer science and the software engineer is basically the mason. So one will now actually what? Design what you call the algorithm, the theory. It's going to develop all those functions for your application. Then the software engineer will just actually will call those applications as building blocks to your application. So they come with what invention? The computer science comes with the invention of how things need to be done. Then the software developer or the engineering will actually implement them. And the nature, as you all know, this one is the theory aspect of the software, and this one is the practical aspect of the software. And what can be computed and how efficiently? So which means that all the functions that, for example, the inbuilt function that you have in, let's say, Java or the C++, is being designed by what? The computer scientists, because they look at the science behind it. And the engineer look at the standardization of using them, the accepted way of using them to build such complex systems. So the computer science can improve algorithms and the models, like this AI model. Then this open AI, the ChatGPT and the likes actually would use them to build their products. Okay, you understand? So the scientists will develop such models, then we actually will implement them in our application. And the analogy also follows as you see there. So in practice, that's what I was telling you, that software engineer, to learn it, it can also be learned as a career. Because whatever you're going to learn here is basically whatever you are going to implement them. Or that's basically what they are going to ask you on the field of what work. So to be a software engineer, you need to have a solid foundation in understanding how theories, algorithms, computation, models are being developed. Then you can apply it safely in what? The discipline of what? Software engineering. So simple. Software engineering is basically now saturated, but then you find your feet when you are much serious. Software engineering, I did computer science, and software engineering was something that I feared most. But look at where I am now. I develop software day in and day out. I'm currently developing a software for Methodist Church, Ghana. Let me show you. Just a moment. Yeah. So I'm just building and I'm testing along the way. So I'm just the 1 man thousand doing everything all by myself. I'm testing, doing everything. So all of this has been being modeled by the computer scientist. Then I will just pick the functions and I will actually use them in building this. Right. Now, as I informed you earlier, what necessitated for the software engineer, it's not as if softwares were not being built. They were being built, but then they were not conforming to a particular standard. So let's go to understand this software crisis and the origins of the software engineering to go a little bit deeper. Now, what was the software crisis which I scratched off? So hardware became more and more powerful and cheaper when you guys did the generations of computer. When we looked at the first generation, second generation, third, fourth, and the fifth generation, where the third generation was full of vacuum tubes, and they actually look at an alternative which was used in the second generation. The second generation is where software development also took shape, where the hardware was basically transistors. So hardware became more and more powerful and cheaper. Organization began commissioning increasingly ambitious software systems because they realized that because of how software was being modeled or how they saw software development, it was seen that there are some things that the software can do effortlessly without the intervention of the hardware. I can give you a practical case which we use today. Back in the days, the number one phone brand was BlackBerry. because it had a full hardware keyboard. This thing to change, and Apple came out with the radical design where it doesn't have a physical keyboard but rather a virtual keyboard. That necessitated for all our phones these days to have a full screen. You understand? So you could see what made our computer hardware to shrink in size, where we now have full screen to do virtually whatever we want without looking at the implications of the hardware. So the results were alarming. Software projects consistently will exhibit the following symptoms. Projects were delivered significantly late, often months or years behind schedule. Projects massively exceeded their original budgets. The delivered software frequently did not meet user requirements because I understand everything was actually in the inception. That's where they realized how powerful software can be. And they were often unreliable, prone to crashes and unexpected failures. And if we see back then, those who were born maybe early 2000s, we had this blue screen, especially with Windows operating system. I think these days you hardly um, you hardly experience such blue screens. Possible and also impossible was software to maintain them. Small changes cause unexpected failures elsewhere. It's true because if certain components depend on other components, a change may affect how the other component need to react. And if all of these were not considered, there's going to be a failure. And at that time, too, the models that they were using to develop applications were not available or were not actually found. Okay, so we have some system design models like the clean architecture, the dependency injection. It's something that you don't know. But then those who will go much into software engineering and development, you actually will hear them and understand them. Okay? Or the solid principle. There are so many design principles. So which means that if you're not following some of these things, developing software is difficult. Let me show you a little one that I have here. So I'm going to show you here. No, no, no. So this is actually a language in C sharp. And let me show you something here. Okay. So we have something called dependency injection. So which means that once I develop something, okay, let's see like a function that calculates or that add two numbers. Now, because it's a function, I can call it anywhere I want. So that if there's a problem, I don't need to call it, I don't need to look at where it is being called. I look at what? The function itself, make the change. Then without being getting affected by the area to which I'm using them. For example, I have this function, not this one. Let me see. Yeah. So you can see that I run this simple function, I wait, and this way I'm calling it. So which means that if I need it, or if there's any modification, I look at this function itself. Okay. I look at this function itself, which it is down somewhere here. I don't really understand, but then just follow it. And if you still want to be curious, I'll be so pleased to show you what I'm doing. So I have it here called the executive, this one. So don't forget the name is to create asynchronous. So the create asynchronous, where is it? Yeah, well, I saw it somewhere here. Let me pull up this one. Yeah, this one. So this is actually the function definition. Okay, so it takes some parameters and do all the logic. So which means that I just need to call it. So that if there's any change, I come and change it. I make a change to the function definition without disturbing where that function is being called. Unless maybe the parameters that it is required, sorry, we need to change as well. So we have different lot of software design models that we use that will make your application very easy to maintain. Okay. Yeah. So these are some of the, and there's no systematic way to measure or to guarantee software quality. So in that scenario, they were able to define the core problem, which they saw to be a gap, which could be envisioned and what could be actually built was going faster than ability to close. So which in that gap of what we want to do and what is actually being built, the gap was getting wider and wider and wider. So they used the term software crisis, which was coined to describe the systematic failure of the software industry to develop quality products on time and within budget. A challenge that we still face today. But because of having this software engineering, at least all software development is actually pegged towards the standard principles, which I will show them to you very soon. I think in chapter 2 or chapter 3. The software development life cycle. The software development life cycle, where all the models implement this cycle. Imagine everybody doing things anyhow. There'll be so much chaos. There'll be so much what? Chaos. Any question, ladies and gentlemen? All right, if there are no questions, now let's see how the software engineering responded. So now the software engineering, out of all this software crisis, now they came out to be a discipline, to have a systematic approach, which was being set up to what? To solve this software crisis by using a standardized, rigorous, systematic, and a way to measure from the inception of the development to the last cycle, which is the maintenance. So these were the key responses that they formulated as a discipline. There should be formal development processes, structured methodologies rather than as and when we feel. Requirement engineering, systematic approaches to capture and validate what the software must do before building. Because, for example, if you are building a house and you don't give the contractor what you really need, the contractor may do something that you didn't even like. And the design principles, like what I was mentioning in the code that I actually exhibited to you, the modularity. Okay, everything is being designed as modules. Then abstraction, and I'm sure perhaps C++ or Java, you guys have done object oriented. Are you doing programming language this semester?
Yes, sir.
Are you having a programming language this semester?
Yes, sir.
Which one is what? Java, right? Okay. Then separations of concerns to manage complexity. So if you look at my application, for instance, you could see that each of them has its, looking at the name, will tell you what it is meant for. I have one here, a simple one here, which this one is for email notification. Then you also have another one for SMS notification. So, which means that we try to separate it, even though they are for sending messages. So you have that kind of separation concern and what you call abstraction. So abstraction is basically something which is not really there physically, but is there. For example, how do we connect to ECG or Akosombo? Akosombo is not in our house, but yet we enjoy electricity services. It's all about what you call the abstraction. Yours is to plug in there. So which means that the ECG company or the will actually now need to develop an interface with specification that if you want to connect to our grid, just use a 3-pin or 2-pin connected to your wall, and that is it. How it will be connected or how the energy will come from across your boat to your house, you don't need to worry. That's what you call abstraction. The ECG is there, but physically not where you want it to be. Yet you are enjoying electricity. So that's what we call the abstraction. And the separation of concern. And you realize that even the ECG, you could see some small places having light out, other places having like yes. You don't put all your eggs in one basket. So that if there's a problem, we know where to tackle. But we don't actually tackle everything as a go. And once there's a separation, it's not really going to be that when one problem, one leg goes off, the entire body system should work, shut down. No. So that's also part of what the software engineering principle that they actually lay down. Now, we also have the testing and quality assurance. The formal process of verifying the correctness. Is it working as expected? And reliability. There was a system which was being developed, and when all users came logging in and started using it, the system shut down, which means that it failed the quality assurance test. Now, let's go to project management, where the cost estimation models, the scheduling tools, and the risk management frameworks. So the cost estimation could be the various items or the tool that we need, and even the model that we are, I mean, the software model, the code model that we are using. What is the cost? Not as in terms of money, but how is it going to cost our project? Is it efficient model that the cost that will be required to finish the project will be it will be uh, in line with our project projection. They may also have what you call the change management, whereby are we saying that one person is allowed to work on a singular task, or you can have two people at most to work on a single task, so that if one person leaves the job, that gap will not be what realized. And the risk management. How do we measure risk management? How do we measure threat risk in developing our projects? Is it that we don't put measures on the software engineer's machine so that the software person cannot steal the source code and go and use it elsewhere? Or if robots attack and get the machine, is this something that is going to worry us? Also, where do we keep our source code? Is it in a secure place that even if your machine is stolen, you still get to what, have your code intact. So if you look at my application, for instance, I'm saving it on what, GitHub. Okay. So which means that I can make the changes and actually upload the code changes into GitHub. So if this machine at worst case scenario got spoiled, I can still have my source code intact without crying that I need to now come out to develop all this from scratch. So all this things forms part of what, project management. So to become a project manager for a software company, it is really a big deal. Then professional standards. So this IEEE and the ACM have come out with what we call the Code of Standards, and also their professional certification program. And recently, I went for a program which was I had this certificate. It was certified. So now I'm currently a certified data protection supervisor. So, software engineering primarily do data because that data, what's the essence of building a system? You understand? So, which means that it is my duty to make sure that user data are actually protected at all costs. And to use a user data, there should be user consent. And processing of user data should also conform with our Ghana Data Act 843. Okay, so it's a very, very important that if you're going to go into this particular field, you need to actually have all this on your fingertips. Why is it important that this software engineering is something that people, all these people sat down to come to formalize as a discipline, but actually what? Telling us what we require as we've seen in the responses, the formal development processes, requirement engineering, design principles, testing and quality assurance, project management, and setting up professional standards. Because a bug and error can be quite, or not can be quite, can be very devastating to human life, catastrophe to human life. It can kill because now modern systems, complex systems, sophisticated systems, critical systems now rely on softwares or software application to run. For example, the banking system where the ATM, you can buy things online, healthcare reports where our online communication, internet, everything rely on these complex software systems. And it's very, very important that we take it very seriously for the fear of the unknown, which the consequences of software failure can lead to what, minor and loss of life and property. So I want to share with you some of the real world scenario that actually led to some software catastrophe to human life. Now, the first one is Ariane, which happened in 1996, which I know most of us we were born or about to be born. So the Ariane 5 is a rocket that actually exploded 37 seconds after launch due to a software bug, all because there was actually a problem converting from 64-bit floating number to a 16-bit integer, causing an overflow. So it's like trying to fit in uh, an elephant to what? A needle pinhole. It will never fit, which actually costed the company $500 million. All the investments, all the sleepless nights has gone into thin air. And the lesson from what we see here is that reusing software without re-engineering it for new requirements is a fundamental software engineer. It's like when they've given us an assignment and you copy or you stole my source code thinking you can use it. No, it may not work in your context. So without proper re-engineering to meet your new requirements and standards, it's going to lead to a software engineering failure. Another one that happened in the 80s, the 85 to 87, where this particular radiation therapy machine delivered lethal radiation overdose to at least 6 patients due to race condition in its software. Those patients unfortunately lost their lives, all because the software didn't have safety engineering practices. So poor software engineering may lead to unaliving people. So it's a matter of life and death. For example, imagine that all the payment that you guys have done at the bank is wiped off. You see how devastating that is going to be. Or the enemy countries that we have in our world, and mistakenly, the guard who is managing those rockets, the nuclear, what, mistakenly, because he was dozing off, then he mistakenly pressed the button to launch. It can wipe off a continent within some few minutes. Okay, so we are not even looking at that, but then we are looking at whereby time is not invested to use software engineering principles in the development of your software. It's very, very critical that we take software development and software engineering as a discipline very, very seriously. Because while the thing works, you are going to be called genius. But if it fails, you may be arrested, fined, or even in prison, or even worst case scenario, you may be executed. Because failure in adhering to the software engineering principles may cost human life or property. That may lead to millions of thousands, millions of dollars, billions of, you understand? So it's very, very important for the following reason. Its economic impact. Now there have been so much warnings about the consequence of human indulgence of using AI. And software development, even the field of AI, consume a lot of energy, where huge investments are being dedicated towards AI. So a poor quality AI model can cost economy, can wipe financial investment stocks to even negatives. And to rework, to resurrect, it's not a joke. A lot of money need to sink in. So we need to be very careful if we are being handed some critical aspect to play. And the safety and the reliability, as you all know, there was an issue that I think somewhere in Russia, one of their nuclear uh, one of their nuclear plants actually got spots. I've forgotten the keyword, but not spot. But then it has been now it does not allow human to stay because the radiation is too strong for human survival. And I think what happened to China or Japan, the Fukushima nuclear reactor, that actually got leaked and had a lot of devastation. And when this autonomous vehicle was being trialed in some of the advanced countries, you realize that it is going in a different direction and actually were malfunctioning at some point in time. So, which means that the demand of software should be of the highest quality and reliability. So, you could see this my software I'm developing. It's like I'm taking so much pains to develop. I'm actually at this side. Okay, I'm actually at this side, and I'm creating. So, as we could see, that I'm just putting some checks for myself, so that, for example, if something doesn't go wrong, I try to consult to see what is missing and what is required. Okay. And I'll being a developer, I'm also see myself as a normal user. But software development in Africa or in Ghana, they don't value us because they feel like, oh, it doesn't take much effort. This one, I see like it's so simple to do. Okay, it requires a lot of brainstorming and sleepless nights to come up with such a software. Okay. And then feel free if you have any question to ask me. Okay. Now we also have the maintainability. So software should withstand the test of time. Okay. And as you all know, software that you have installed on your phones and machine get updates every now and then. And for those who have been in this field for such a long time, sometimes updates may not go according to plan. Even let's say the bank that we have, sometimes we receive a message that there's going to be an upgrade maintenance, and when you wake up, they will tell us the upgrade was not successful because after updating it or after maintaining it, it's giving us unforeseen errors that we never anticipated. Okay, so there was this software which was being developed that is going to manage students' admissions. So instead of the human trying to now evaluate your um your admission, I mean your results and those things, that system was developed to automate it. So we need to feed in the cutoff point, all the information that is required. But it worked to our expectation, but then there were other flags that the system failed to capture. For example, I think you may see some of the results being shown as what withheld, whatever. But whoever was developing didn't actually look into the answer. They were looking at only the grade, whether he had B plus, but he never knew that the withheld, those information were part of what? Something that they should have anticipated. So the system failed massively, giving admission letters to um, undeserving students. You understand? So quickly they need to what, write to them that they should ignore, and the system or that feature was shut down. You get it? Now, so it's very, very important that we need to make sure that we need to test rigorously on all scenarios before we migrate to the live production.